Okay, for the beginning of this lecture, we begin in, again, this is chapter 5, and we begin with the section on this is the section on various other types of force that we're getting an introduction to, and many of these will be treated in greater detail in later chapters, which we may or may not get to this semester. We'll see. And the first one is friction. As we've already dealt with friction in several problems. Friction is basically a force that resists movement or potential movement. Its direction will be opposite to the direction of motion or potential motion. Sometimes if the friction force is large enough, it can actually prevent motion. But in that case, it would be acting in the direction opposite to the potential motion or the direction that things are trying to move in. And that is detailed in the next chapter, chapter 6, and we will definitely get to that. So we'll wait till later to go into more detail about that. There's also a little section on spring force. Spring is a spring, not the season, unfortunately, but the mechanical device known as a spring is basically a connecting medium that has the ability to restore its shape after a force is applied and released. So the spring deforms while the force is being applied, and then it springs back into shape once the force is released. The spring essentially does that by exerting a restoring force, which goes in the opposite direction to the force that was applied to the spring. Okay, springs can work in either compression or extension. So you can squeeze a spring or you can pull it out further. And just a good convenient example of a spring is right here in a ballpoint pen. Whoops, see, there's a spring right there. And I can push the spring together. This one's a little wobbly, so I'm going to hold it straight when I do that. It's still a little wobbly. But when I let go, point, point, it springs right back. I'm applying a force. Let's apply it only in one direction for argument's sake. I'm applying a force from right to left in this case, and I can feel the spring pushing back on me, and that's the restoring force. And the restoring force is going from left to right in the opposite of the direction I'm pushing it. On the other hand, you can pull a spring also, and so I can pull it toward the right, and I can feel it resisting my pull, and what's resisting it is, again, the restoring force. So if I'm pulling the spring to the right, the restoring force is pulling the spring back to the left. And I can stretch it out, but I let go, and it springs right back to its original shape. Within limits, each spring has its own elastic limit. That's what that's basically the maximum amount of force that you can apply to the spring without deforming it permanently. So if you apply too much force to a spring, you can permanently stretch it or permanently compress it. Okay, try to get this thing back together. All right, there. And so we use springs in things like ballpoint pens, the kinds with retractable points. And the spring is what basically pushes the point back against the stop so that the ink filler is not hanging out the end when you try to use it. There is a law that represents the relationship between the applied force and the extension of a spring, and that's known as Hooke's law. Hooke's law says that the force that's applied to a spring is equal to negative kx. Okay, k is known as the spring constant or the Hooke's law constant, and it's a measure of stiffness. The presence of this constant, so in other words, if we're saying that the force is equal to a constant times the amount by which the spring stretches or compresses, that implies that the force must be proportional to the stretch or the compression. And it is. If you apply twice as much force, the spring will stretch twice as much. It also implies that the spring, well, has a directly proportional, or in other words, linear response to force. So like I was saying, if you double the force, you double the extension or the compression of the spring. Most springs act like that, but there are some springs, some high-tech springs that actually have a nonlinear response to force. And so they will have different values for K depending on how far you compress or stretch them. And I know one place springs like that have been used. I'm not sure if they are still right now, but in the recent past anyway, some of these nonlinear springs were used in the suspension of the Corvette, which improved the handling because they got progressively stiffer as they were compressed more and more. But most springs don't do that. They basically have a linear response between force and the extension or compression of the spring. The spring constant is often considered a measurement of the stiffness of a spring. So when we think of a spring being really stiff, what we really mean is that it's really hard for us to compress the spring. So in other words, you have to apply a lot of force in order to get the length of the spring to change even a little bit. So that would be a high value for K, and that would mean a very stiff spring. On the other hand, some springs, like the one I just took out of the pen here, have a very low value for the spring constant, meaning it takes very little force to change the length of the spring by a certain amount. And that would be a spring that's not very stiff at all. It's negative because actually in this case, F is the restoring force of the spring rather than the force that's being applied to the spring. And the restoring force, as I mentioned, is in the opposite of the direction that the spring actually moves. So if you're stretching the spring, the restoring force is trying to pull it back. If you're compressing a spring, the restoring force is pushing against you. And that's why K is negative. Okay, let's see. The units for K would be newtons per meter. Okay. So in other words, amount of force per distance of extension or compression on the spring. All right. So if you know the force and how much the spring stretches, finding K is just a matter of algebra. Or say if you know K and how much the string stretches or compresses, then you can find F. Quite easy. If you know the force and the spring constant, then you can find how far the spring should stretch by rearranging the equation a little bit. If we have, we'll diagram some situations here. If we have a situation where a spring is relaxed at its equilibrium position, that is the position that it would normally be in if nobody is exerting any force on it. And if you then compress the spring by pushing it this way to the left in this diagram, you can compress it by a certain amount, which we'll call delta x1. Delta x meaning the distance that is compressed, and just 1 meaning the first example. This would be compression, and the restorative force would be negative K times delta x1. On the other hand, you could take the spring and stretch it from its equilibrium position by pulling it, in this case, to the right, and the restoring force would be pulling toward the left, and you can calculate the restoring force by negative K delta x2. Delta x2 in this case being the distance by which we've stretched the spring versus its equilibrium position. Okay. You can also, even though F in this equation is the restoring force, you can easily calculate the force applied, to the spring, because it would have the same magnitude as the restoring force. It would just have the opposite sign. So F is the restoring force, but the force applied to the spring would just be the same number with the opposite sign. Okay. And finally, in this chapter, there is a little bit more on drawing free body diagrams. We've seen quite a few examples of that, and the examples that we've seen so far have been pretty simple and straightforward. But there are many cases where drawing the free body diagram is not that simple. And so this section sort of helps us choose what should be included in the free body diagram, and kind of helps us decide what the system should be. Because if you choose the system wisely in a problem, then you can eliminate a lot of the complications that might otherwise arise. If you choose the system poorly, then you end up with a lot of different factors that you have to take into account. And it is still possible to solve the problem, but it'll be a lot harder than it needs to be. So drawing free body diagrams is important in solving problems because it's a good summary that can be understood at a glance of the object you're concerned with and what are the external forces on that object. And by drawing the forces proportionally and at the proper angles, you can get a pretty good idea about what's going to happen even without doing the calculations. Remember that free body diagrams should include only external forces on the system. So forces that are applied from outside onto the system. Internal forces within the system should not be included in a free body diagram, and forces applied by the system on the surroundings should not be included in the free body diagram. Remember, according to Newton's third law, for every action, there is an equal and opposite reaction. Anytime there's a force being exerted by the surroundings on the system will also be exerting a force back onto the surroundings. And we only want to count one of those. And that would be the force on the system, not the force by the system. So it's only external forces on the system that you want to count, because that's what affects the movement of the system. And then you can apply Newton's laws to the diagram. Okay, to be more detailed, the first thing you'd want to do in drawing a free body diagram is draw the object of interest. And I said schematically, meaning that it doesn't have to be really accurate. It doesn't have to be really artistically spectacular, although I think a lot of people in this class do seem to have quite a bit of artistic talent. So you can make it as beautiful as you want to. But really, if it's a person, then that right there is good enough. That's really all you need. Okay, so anything from there on up is okay. You want to focus on the forces acting on that object from the outside. That's what I was saying up above. Outside forces on the system. That's what you want to focus on. You can you can even go as far as representing the object as a point, as long as its size and shape don't matter toward the problem, and as long as it's not rotating. So this person, as long as the forces of the system don't really matter, the size and shape of him doesn't really matter, you could represent him as a point. And you usually try to draw the point at the center of mass of the object. So, with a person, it would be probably, maybe about halfway up. Okay, so then you can choose the axes. Which direction is the x-axis going to go in? Which direction is the y-axis going to go in? Do you need a z-axis? If it's a three-dimensional problem, then you need a z-axis. You'd include all of the forces acting on the object as vectors. And again, you'd want to draw the forces as close as possible to being in proportion to each other. So if one of the forces is twice as big, the arrow for that vector should be twice as long. and you want to draw them as close as you can to the correct angles at which they're acting upon the system. Okay, don't include the net force. And again, don't include internal forces or forces by the system on the surroundings. Okay, let's see. And don't include both of the forces in any action-reaction pair. Again, just the forces exerted by the system on the surroundings. Then you would determine and draw in the X and Y components of the forces. And they recommend that you cross out the original vector so that you won't think that that's still in play, so that you won't think that it's still, once you've got the X and Y components, you don't need the original vector. If there's more than one object involved, as there will be in some of these examples, like for instance, this one right here, then you can draw a separate free body diagram for each object. So just some quick examples. If you have a sled that's pulled by a force P, presumably representing pull, at an angle of 30 degrees and the mass is 15 kilograms, you could draw the sled like so, which is, a fairly schematic sled. It kind of sort of looks like a sled. And you could choose the axes. Usually, in most cases, you'll have the x-axis being horizontal and the y-axis being vertical. And in this case, that makes sense, since the movement of the sled is going to be in the horizontal direction. It makes sense to have one of the axes going that way. But you can also draw the sled as a point. And in fact, when doing an actual free body diagram, it's probably easier to draw something as a point than as trying to make it look like what it actually is. So if you have the center of mass of the sled, you've got pushing downward, you've got the weight of the sled, and then pushing upward, you have the force of the earth pushing back on the sled's weight, or in other words, the normal force. And since the sled is not accelerating vertically, either up or down, you can assume that the weight and the normal force cancel each other out. And since we're concerned about movement in the X or horizontal direction, you don't really have to worry about the weight or the normal force. And then also we've got the pulling force, which is at an angle of 30 degrees to the horizontal. Because the pulling force is at an angle, you would want to resolve that into its X and Y components. The weight and the normal force are already resolved into their X and Y components. Both of them, the weight and the normal force, are both all Y component with 0 as the X component. But for P, you need to find the X and Y components. And once you've found PY, that's this arrow pointing straight up, and PX, that's the arrow pointing to the right, you can cross out the original P, which is what this mess here is. And of course, I'm including the normal force and the weight for completeness. But like I said, if we're concerned about the sled moving horizontally, then the weight and the normal force don't really have any effect. Another example is the example of two blocks on an inclined plane. This looks like a fairly simple setup, but it gets kind of complicated. So we want to construct a free body diagram for box A and box B in this figure. We've got an inclined plane, and we don't have any numbers here because we don't need to figure out a numerical answer. We just want to set things up with the free body diagram. And in doing that, we've got box A on top of box B, and box A is being held to the wall by some sort of cord. Okay. We also, of course, have gravity pulling downward, and gravity will have a Y component and an X component, which will tend to be pulling box B down the inclined plane, while the cord is tending to pull everything, or box A anyway, up the inclined plane. So for box A, we can draw a free body diagram, sort of like this, where we have the point being the center of mass of block A, and we have the line or the cord, which has a certain tension in it, and that's the force that's tending to pull the box A up the ramp. And also, we have the force of block B on block A. That's what FBA is. And that is tending to try to pull block A down the ramp. Because block A is sitting on block B, it's not sitting on the ramp. So it's actually block B that's tending to slide down the ramp, and it's the force of block B on block A that's tending to counteract the tension in the line that's pulling A up the ramp. Also, we have the weight of block A, which will be pushing straight down. And we have the normal force of block B pushing back on block A, which is normal to the surface of block B, which means it's not parallel to the weight vector. Now, of course, in these situations, we haven't gone as far as choosing what the axes are going to be. You'd probably want to choose the x-axis as being the surface of the plane, or parallel to the surface of the plane, the inclined plane. And then the y-axis would be perpendicular to that. And then we would have to figure out the x and y components of the weight. Okay, but we're not going that far. We're just drawing the free body diagram. For box B, we have, in the true free body diagram, we have a point representing box B, and we have, okay, we have the weight of the box, which is pushing straight down. We have the normal force on box B from the ramp, which is perpendicular to the ramp, and so it's not parallel to the weight vector. And of course, because of this, we would want to find the x and y components for the weight vector, because again, we're probably going to choose the x direction as parallel to the ramp and the y direction as being perpendicular to the ramp. Okay, we've also got FAB, that is the friction of box A on box B, which is tending, since box A is anchored to the wall by that cord, the friction of box A against box B will be tending to pull box B up the ramp. And there's also little FB, that is friction of box B on the ramp, or sorry, the friction of the ramp on box B actually would be probably better way to say it. And that tends to pull the box up the ramp also. And then we also have the normal force of box A on box B, which is parallel to, but pointing in the opposite direction of the normal force of the ramp on box B. And pulling the box B down the ramp, you would have the x component of the weight. So that's why it doesn't show any force here going down the ramp for box B, because we haven't found the x and y components for the weight yet. But that would probably be the next step. Okay. And that's as far as we wanted to go, because we were really only concerned about drawing the free body diagrams. Now we have another situation that's going to come up again in the next chapter, and that is two blocks in contact, or sorry, it's this one that's going to come up. Two blocks in contact with each other, and you have a force, oops, sorry, it's up here. Two blocks in contact with each other. You have a force that's applied to two blocks that are in contact. So a block with mass 1 and a block with mass 2 are in direct contact with each other, and they're being pushed toward the right with a certain amount of force. And that's what this vector is here, F. if you want to do a free body diagram for the block with mass 1, again, you could represent the block as a point, and you would have force F pushing the block toward the right. And you would have the reaction force, or basically A21 is the reaction force of block 2 on block 1, and that would be resisting the force pushing the blocks to the right, because this block 2 has a certain amount of inertia, and so it's going to take basically, that's like, it's similar to exerting a force backwards. And then you have the weight of block 1 pressing down and the normal force of the floor or whatever it's on pressing back up again. Okay, for block 2, what you've got will be the weight of block 2 pressing down and the normal force of the surface pushing back up again. And you have the reaction force of block 1 on block 2. That is block 1 pushing against block 2. And that's what's pushing block 2 to the right. And so those are all of the forces that are of relevance in figuring out the movement of block 2. And finally, the example that will come up in the next chapter is a block on a table coupled to another block hanging by a pulley. So we have a block with mass 1 and a cord whose mass we can ignore, attached to a pulley whose mass we can also ignore, and we can assume that the pulley has no friction. And hanging from that cord is a block with mass 2. And mass 2 will tend to be pulled by gravity downward, and that will have the effect of pulling mass 1 to the right. And of course, the cord will have a tension in it. Because of the cord between them, the blocks are coupled. So mass 2 exerts a force on mass 1 because of the weight of mass 2 being pulled down by gravity. And that causes the entire system to accelerate. Mass 2 accelerates downward, mass 1 accelerates to the right. Their acceleration, assuming the cord doesn't stretch, their accelerations should be the same as each other. So a free body diagram for block M1 would look like this. You could use a point to represent the block or draw it as an actual, square. You would have the tension in the line pulling block 1 to the right. And also you would have the weight and the normal force. So that's block 1. The free body diagram for block 2. On block 2, you have the tension in the line, which would be pointing upward. In this case, and downward you would have the weight of the block, or mass 2g, mg, because weight is mg. As long as the string doesn't stretch and doesn't get loose, then when I said a moment ago the accelerations should be the same, I was talking about the magnitude of the accelerations, because technically mass 1 would be accelerating to the right, which is usually considered the positive direction, while mass 2 would be accelerating downward, which is usually considered the negative direction. So actually, in terms of actual numbers, A1 would be equal to negative A2. But the tension should be the same throughout the entire line. So that's for mass 1 and mass 2. Okay, I went a little long on the first segment, but that's because this is the end of chapter 5, so I thought I'd squeeze it all into one segment. So we'll come back in a moment with the beginnings of chapter 6.